Hello and welcome to everybody attending this talk. I am Sinchan Sengupta and I will be presenting our paper titled A Self-Stabilizing Minimum Average Stretch Spanning Tree Construction. So this is a joint work with Sathya Peri and Parwat Singh Anjana from the Department of Computer Science and Engineering, Indian Institute of Technology, Hyderabad. Okay. So let us look at an example and understand the concept of stretch first. So suppose we have a graph as shown here with certain edge weights. We assume a spanning tree T on this graph. Now we compute certain distances on both the graph as well as the spanning tree. Let us say for the pair of nodes A and C, the distance in the graph is 2. However, the distance in the tree is 9. Stretch is defined as the ratio of the distance between two nodes in the tree to their distance in the underlying graph. For the pair AC, the stretch is 9 by 2, which is equal to 4.5. It can be seen that the best stretch value we can get is 1. So look at the pair AB, for example. They are directly connected in the tree and their ratio is 1. This is indeed the minimum value one can get, since tree distances are always lower bounded by graph distances and the ratio cannot go below 1. Okay, so now we look at the problem we want to address in this work. This is about constructing a self-stabilizing spanning tree that minimizes the average stretch for all the edges in the graph. In short, the spanning tree minimizing the value lambda in this equation is the desired output. So the general problem of constructing a MAST, however, is NP hard. For an example, we go back to the same tree we had. Its average stretch is computed here. The pairwise stretch values for all the edges are enumerated at top right. We just sum them up and then divide it with the cardinality of the edge set to get the average stretch of T. If this T has at least, if this tree T has the least average among all the other possible trees in G, then this is the MAST. Right, so the lambda of T comes out to be 2.09 in this case. If 2.09 is the least value we get among all the trees, then T will be the MAST for this example. Okay, so now let us look into a gentle introduction to self-stabilization. So self-stabilization is a non-masking fault tolerance technique introduced by Dijkstra in 1974. The main aim of this technique is to make the system perform correctly in the presence of transient faults in the network. Okay, so regardless of the current state we are in, we somehow want to ensure that the system maintains a valid configuration after the faults have subsided. Okay, so this is the main aim. Now, what kind of faults are we talking about here? So these are transient faults that are basically temporary, and they cause network disturbances that can arise from, let's say, voltage fluctuations, bit flips, etc. The main assumption is that the time for repair or stabilization is much less than the time between the faults. Otherwise, they won't subside, or we cannot reach a valid state ever. So now we discuss a stronger version of self-stabilization called the silent stabilization. Okay. So this was introduced by Dolev in 1996. Here we say that an algorithm is silent self-stabilizing when the values in the variables or registers do not change after the system has converged to a correct state. This quiescent state of the system changes as soon as errors are encountered. So silence, silence reduces the design complexity of the algorithm. So there are some distinct advantages, as we can see, and it is very much suited for graph algorithms, much like the one we have in hand. Okay. So now we move on to the technicalities of how to represent self-stabilizing algorithms. So in this work, we would represent the rules of the algorithm in the form shown here, where each rule comprises of a Boolean predicate called the guard, and an action follows it. A node satisfying its guard predicate is called enabled. The model we use in our work is the locally shared model with composite atomicity. The assumptions here are that each node is allowed to read its own variables and that of its immediate, or we call it distance one, neighbors. But however, every node has the power to modify its own variables only. Okay, so the scheduler responsible for selecting which subset of enabled nodes will execute the self-stabilizing algorithm is called the daemon. In this work, we choose the most general daemon known as the distributed unfair daemon. So it has no strong assumptions, and we give no specific preferential treatment to an individual node. This leads to asynchronicity. So next, we look at the performance metrics. For time, we use the notion of rounds, where each round comprises of a lockstep execution of 3 actions. A node can receive messages from its neighbors, perform some internal computations, and then send messages back to the neighbors. And the space required is the number of bits needed at each node. Okay. So now let's discuss an important construction in our algorithm that we'll be using in our algorithm. The main aim of our design protocol is to construct a distributed cluster tree from the underlying graph. So what we do is this: we divide the nodes of the graph into a number of subsets and call them clusters. So let us see some of the properties of these clusters. The clusters are constructed in such a way that they are pairwise mutually exclusive, and their union gives the entire vertex set of the underlay. Each cluster will have a cluster leader, which is the node with the lowest ID in that cluster. Okay, so additionally, each cluster will have a low diameter, and the number of intercluster edges will also be bounded by a certain quantity. We can also note that each cluster is abstracted as a single supervertex, and its magnified view is shown in the diagram here. So the path between nodes X and Y will possibly go through many intra and intercluster edges. So our main claim is that such a construction of DCT will be a low average stretch spanning tree. Okay. So coming to the related work section, our BuildT protocol derives inspiration from the seminal Alon et al. Algorithm. They had given a MAST construction with an average stretch that is exponential in the order of under root log n log log n. So their technique involves creating, let's say, K clusters with certain diameter bound, and constructing an intra-cluster BFS tree for each cluster. This was recursively performed until the entire graph was kind of done. So our approach is somehow similar to this, and we use self-stabilizing DCT to achieve this work. Okay, so the main contribution of this work can be summarized in the following results. So the first theorem states that the DCT construction used in our algorithm generates an MAST with an average stretch of n power order 1, or a stretch polynomial in n. Okay, and the second theorem states that the proposed protocol terminates this construction in order of n plus delta into eta asynchronous rounds, where delta is the maximum size of a cluster and eta is the number of clusters in the constructed DCT. Okay, so now we explain our solution in brief. So as mentioned already, our solution involves creating the DCT. Now, the DCT consists of two kinds of trees in it. One is the intra-cluster BFS tree rooted at the cluster leader, and second, the inter-cluster tree, where the nodes are the clusters themselves. All right. So to model this, we need to maintain two trees separately. So the first intra-cluster tree is given by the variable parent of X, and the second tree is given by cluster parent of X. So together they represent the entire DCT. They give the parent-child relationship of every node in the two trees. So through these two variables, each node maintains two parents in its memory. Okay, so the next is the status variable. A node checks if it is in a correct state with respect to its distance variables for both the trees. If the node is in a correct state, then it has a status as designated by the uptag symbol. If the node detects an anomaly with respect to its position value or its distance value, it assigns a value of -1 to its status. Further, what it does is the entire subtree rooted at that faulty node also comes under the scanner, since those nodes may also be corrupt. Hence, they are assigned the value of 1, which indicates that the entire subtree is corrupt, and a node of status -1 is the root. Okay. So now we look at certain predicates that help us detect a faulty node. So the first one is incorrect tree root. A node is an incorrect tree root if it has a status different from its parent, or it is a parent that is not one of its immediate neighbor, or it has a faulty distance value with respect to its intra-cluster BFS tree. Okay, so if it evaluates to true, then this node is somehow faulty. The second predicate, incorrect cluster root, is similar to the last one, but written in terms of the inter-cluster tree. Okay. So the next set of predicates, intra-cluster correction and outer cluster correction, involves the nodes checking if a neighbor exists in its one neighborhood of either the inter or the intra-cluster trees. That can give a better distance value to the entire DCT. So if it is available, then it evaluates to true. The check diameter predicate here finds out if it is safe to add a node into a cluster. It checks if the diameter does not exceed its predefined bound after adding, let's say, a node U into the cluster of V. Okay. The predicate check intercluster edge evaluates to true if each cluster is a bounded number of inter-cluster edges incident on it. The value of 8 log n by d is the bound we are talking about, where d is the diameter of each individual cluster of the entire graph. So d is the diameter of the entire graph, and diam is the diameter of the individual clusters. Okay, so now we describe the working of the BuildT protocol in brief. So the error in the node is detected using the predicates which we described before. Okay, the faulty node detects the errors and freezes itself and the subtree rooted below it by assigning the status of -1 and 1 respectively. Okay. The correct distance values are assigned to the leaves and goes up the subtree until the rectification process reaches the root, which is itself corrupted. Okay. The free subtree is released from its lock, and this rectification is done iteratively every time an error is detected. Okay. So for the actual rules, you can refer to the algorithm 2 of our paper. So now we discuss the stabilization time in terms of rounds. So let delta be the maximum cluster size and eta be the number of clusters we get after the entire DCT is formed. So the rectification of intra-cluster distance values takes a total of 3 times the cardinality of TU, where TU is the subtree rooted at node U, these many rounds. The rectification of inter-cluster cluster distance values takes a total of eta into delta rounds, and each new cluster joining request takes order of n rounds. So if we total them up, we have 3tx plus delta eta plus n rounds, which is the same as order of n plus eta into delta rounds. Okay, so now let's sum up what we have discussed so far in this work. So to the best of our knowledge, BuildT is the first self-stabilizing solution for the MAST problem. It generates an MAST of n to the order 1 average stretch and terminates in order of n plus delta eta asynchronous rounds. So as future possible, so as a future work, we would like to analyze the complexity in terms of steps or moves. So it is often done for silent self-stabilizing algorithms. Also a bound on delta into eta in terms of n would be a nice result, since it would give us the termination measure in terms of the size of the input graph. So thanks a lot for listening to this presentation. We would like to thank the anonymous reviewers whose comments were very helpful. We would also like to thank the organizers of the conference for such a nice overall experience. Thanks a lot.